In this video, we're going to work on a few practice problems related to IR spectroscopy. Now, I did create another video on IR spectroscopy basic introduction. I recommend that you watch that first before trying these problems, if you haven't watched it already. So let's begin. Given this IR spectrum, which of the following molecules would best correspond to this graph? So one of the first things we could see is that we have a carbonyl CO stretch near 1700. Now, all of the molecules that we have in our answer choices contain the carbonyl functional group. So that really doesn't help us. Now, we do have a very strong, very broad OH stretch between, looks like 2700 to 3300. So this indicates an OH functional group, which means we could eliminate answer choice B and answer choice C, which don't have it. So when you have the carbonyl CO stretch and the OH stretch combined, that's a good indication that you have a carboxylic acid. So right now, we're between choices A and D. The difference between choice A and D is the presence of the triple bond. Now, it's important to know that the C triple bond C stretch occurs at 2200. We don't have any signal at 2200. Therefore, we could eliminate answer choice D. So we could say that this particular graph corresponds to answer choice A. Now let's work on our second problem. Which of the following molecules corresponds to the IR spectrum that we see on the screen? Is it A, B, C, or D? By the way, for each of these problems, feel free to pause the video and work on it. And once you have your answer, just play the video to see if it's correct. So the first thing that we can easily identify is the presence of the carbonyl functional group, that is the CO stretch at 1700. And for all of the answers, we either have an aldehyde or a ketone. Now, what else can we identify in this graph? Well, we do have our alkane CH stretch, which is present in every molecule. But note that we have a signal here around 2700. This is the aldehyde CH stretch. So we know we don't have an ester or a ketone or anything like that. We have an aldehyde. Thus, we can eliminate answer choice A, which is the ketone, and D, that's also a ketone. So only answer choice B and C have the aldehyde functional group. So we're between those two answer choices now. Now, what else can we see? Well, for one thing, we don't have a very broad OH signal. So that would eliminate answer choice C because that has an alcohol. We don't see that OH stretch. What we do see is a C double bond C stretch roughly around 1600. So this is it right here. And we do see the alkene double bond CH stretch around 3100. So this tells us that we have an alkene with a hydrogen on the double bond. So that would correspond to answer choice B. So answer choice B represents the molecule that best corresponds to this graph. Now let's move on to number 3. Identify the molecule that corresponds to this IR spectrum. So what do we see here? Looking at our answer choices, we have either an alkane, or an alkyne. And we have two different types of alkynes. We have a terminal alkyne, where the triple bond is at the end of the molecule, and we have an internal alkyne. Well, we have our typical CH stretch at 2900, which can be found in any one of these 4 molecules. But note that we have a signal here around 2200, and this corresponds to the C triple bond C alkyne stretch. So we do have a triple bond in this problem. We have an alkyne. So we could eliminate answer choice B and C. The question is it a terminal alkyne or an internal alkyne? To find that out, we do have another signal here, which is around 3300, and this corresponds to the alkyne CH stretch, which is only present for a terminal alkyne. The internal alkyne doesn't have a hydrogen attached to the triple bonded carbon atoms. So D is out. Therefore, answer choice A is correct. So that's how you could distinguish a terminal alkyne from an internal alkyne. It's the presence of the signal at 3300. Now let's move on to our fourth example problem. So looking at our answer choices, we have a ketone, an ester, an aldehyde, and an amide. Which of these functional groups correspond to the graph that we see on the screen? So let's identify the signals that we have. So we have an alkane CH stretch with a signal of around 2900. And we do have a carbonyl stretch, or carbonyl CO stretch, with a signal at 1700. Those are the two main signals that we have. So with this information, can we identify the right answer? Well, all of the answers have a carbonyl functional group. However, it helps to know what other signals should be present for the other functional groups. Looking at answer choice C, we have an aldehyde. We don't see the aldehyde CH stretch at 2700, so we could eliminate answer choice C. Now looking at D, we have an amide. We don't see the signal for the NH2, which should appear as a double peak around 33 to 3500. So we could eliminate answer choice D. Now looking at answer choice B, we have an ester. An ester would have a CO signal somewhere between 1000 and 1300. Since we don't have that signal, we know that we don't have an ester. So by elimination, the answer has to be a ketone, because this is all that will be present for a ketone: the alkane CH stretch and the carbonyl CO stretch at 1700. So A is the correct answer choice for this problem. Now let's move on to the next problem, number 5. So looking at our answer choices, we have an amine and we have a few benzene rings. So which of these answer choices will best correspond to the graph that we see? Is it A, B, C, or D? Well, the first thing we can notice is the signal at 33 to 3500. We have the double peak, so this corresponds to an NH2 group. So thus we could eliminate answer choice C because we don't have two hydrogen atoms on the nitrogen. Now how do we distinguish between A, B, and C? Well, we do have a C double bond C signal close to 1600. So this could be an alkene or a benzene ring. Answer choice B doesn't have that, so we could eliminate B. Now we do have a CN signal between 1000 and 1100, but that won't help us in this problem. There is one signal that can help us to get the answer. And you might be thinking it's this signal, but this is just the double bond CH stretch, which can be found in alkenes, but also in benzene rings. And for answer choice A and answer choice D, we have that. So how can we distinguish between A and D? Think about what we don't have, what's usually here. What we're missing is the alkane CH stretch at 2900. Answer choice A has the alkane CH stretch right here. Answer choice D, it doesn't have the alkane CH stretch. So because we don't have that signal at 2900, we can eliminate A, because A would have that signal at 2900, but D doesn't have the alkane CH stretch. So answer choice D is the right answer. Now let's consider number 6. So looking at our answer choices, we have an ester, an ether, and a ketone. And we also have a benzene ring. Which of these would correspond to the graph that we see? Well, the first thing that we can notice is we lack the presence of the carbonyl group at 1700. So right there, we could eliminate answer choice A and answer choice D. Now, looking at answer choice B and C, we have two ethers and a benzene ring. Automatically, we don't have the signal at 1600, which would give us the benzene ring, nor do we have the signal at 3100, which will give us the CH stretch of the hydrogen attached directly to the benzene ring. So we have none of those. Therefore, that tells us that we can eliminate answer choice C. Now for answer choice B, we do have the CO stretch. This is the sp3 CO stretch between 1000 and 1150. So that would correspond to answer choice B. Answer choice A, it has the sp3 CO stretch, but what we lack is the sp2 CO stretch. This sp2 CO stretch would show up at a signal between 1200 and 1300, but we don't have that. Nor do we have the carbonyl stretch at 1700. So we can completely eliminate answer choice A. So only answer choice B would make sense. So that's how you could easily identify an ether using the presence of this CO stretch. So that's basically it for this video. Now you know how to use IR spectroscopy to quickly identify the functional groups that would correspond to a particular IR spectrum. Thanks for watching.